Okay, this is a video on 5.3, and we're going to be evaluating trig functions. But I want to start off with how you discuss trig in geometry here. And I have these right triangles, and let's find the sine of, say we did the sine of angle A. The sine of angle A, we could say, is equal to BC over AC, but we also could say it's equal to EG over AG, but it's also equal to DF over AF. And if we look at these kind of three triangles that are embedded in with each other, they're similar triangles. And so it makes sense that the sine of that particular angle could be equal to all those ratios. In similar triangles, the ratios of the sides, corresponding sides, are the same. So going back to how you originally defined the trig functions, and we talked about SOHCAHTOA, or you remembered it. Sine of, so it's still, we can still think about, in other words, we talked about trig in terms of X, Y, and R, but it still holds true that when we have a right triangle, we can think about it as sine of A being the opposite over hypotenuse, cosecant being the reciprocal of that, hypotenuse over opposite. You've got cosine is adjacent over hypotenuse. Its reciprocal is secant, so hypotenuse over adjacent. Tangent, opposite over adjacent. And cotangent adjacent over opposite. So just reminding us of talking about right triangle trig in terms of that. And we'll do that, when we have we're not always going to be working in the coordinate plane or with the unit circle. Sometimes we're going to be doing applications where we're just working with triangles. Okay, so given that, we've got a right triangle in example 1. Why doesn't everyone, you can pause this and evaluate the sine, cosine, and tangents for angles A and angle B. And then come back and let's see what we got. Okay, so we should have had sine of A equals 28/53. Sine of B is 45/53. Then you've got cosine of A is 45/53. And cosine of B is 28/53. And finally, tangent of A is 28/45, while tangent of B is 45/28. Okay, so what do you notice here? Do you notice that any ratios are the same? So taking a look at your answers here, hopefully you notice, and let's see if I can highlight this here. You've got sine of A being 28/53, but 28/53 is also cosine of angle B. Similarly, you've got cosine of A and sine of B being having the same ratio, and finally, and no, the others are reciprocal. Sorry. Almost on there. Well, so it turns out that sine and cosine have a particular relationship. And to see this a little bit better, let's label, I'm going to go into this triangle here. And if I were to call A theta, what's the relationship between A and B? And this comes from the fact that the interior angles of a triangle sum up to 180. We know we already have a 90-degree triangle, so a 90-degree angle, rather. So if A is theta, then we're going to say that B is 90 degrees minus theta, or if we're in radians, pi over 2 minus theta. So thinking about that, instead of using angle A and angle B, again, we saw that sine of A equals cosine of B. So sine of A equals cosine of B. Well, let's replace this with what we just labeled A and B as. We've got sine of theta is equal to cosine of 90 minus theta. I could have labeled b theta, and then a would be 90 minus theta. So the opposite holds true as well. So cosine of theta equals sine 90 minus theta. Well, it turns out these are indeed identities, and they're called the cofunction identities. So sine and cosine go together. Well, it also turns out that secant and cosecant have the same relationship, and tangent and cotangent as well. And try to convince yourself of that. But you can find the sine, you can find the secant and cosecant of A and B in this case, and same with tangent and cotangent. All right, well, let's go to this next page here, and we're going to actually write out cofunction identities. So we're adding to, we did 11 identities the other day. We're now adding to this. We answered this first function about what we noticed about sine A and cosine B and sine B and cosine A. So now let's write out what these cofunction identities are. So we've got sine theta, as we just did, cosine 90 minus theta. And similarly, cosine of theta equals sine 90 minus theta. And then secant of theta equals cosecant 90 minus theta. And cosecant theta equals secant 90 minus theta. And finally, we've got tangent of theta equals cotangent 90 minus theta, and cotangent theta equals tangent 90 minus theta. And we could replace this with radians too. Instead of using 90, we would say pi over 2. So let's just do a little, and we're going to use this much later on, but this was just kind of a good place to introduce these cofunctions. Sine of 9 degrees, it's asking me to write it in terms of its cofunction. The cofunction of sine is cosine. So sine, remember, sine of an angle is equal to cosine of 90 minus that angle. So sine of 9 degrees will be the same as cosine of 81, or 90 minus 9. So cosine of 81 degrees. Cotangent and tangent go together. So cotangent of 76 is the same as tangent of 90 minus 76, which would give me tangent of 14. And cosecant and secant go together. They're cofunctions. So cosecant of 45 is equal to secant of 90 minus 45, or secant of 45. Okay, so more to come with that. So just a few other identities, and just reminding ourselves a little bit about right triangle trig. Okay, speaking of right triangles, let's also do a throwback to geometry when we talk about our special right triangles. These are the 30, 60, 90 and 45, 45, 90 triangles. I'm going to talk about it a couple ways. I like to, and when we talk about what we're going to do today, I'm going to give you a couple of methods to think about it. Some of it comes from how I was taught trig, and some of it comes from kind of working with students all this year and seeing what other people like and other teachers do. So hopefully you'll find something that works for you. All right. So going back, let's start with the 30. We're going to create this 30, 60, 90 triangle, but if I have this equilateral triangle here. So equilateral triangle means the angles are all 60. Need it to be a little bit bigger. And let's drop an altitude. And remember, when I do that in a equilateral triangle, that altitude will bisect that base here. And it also will be bisecting that angle from the vertex where it originates from. So this is going to result in me having a 30, 60, 90 triangle. Now, if the sides here were all 1, so we'll just make it easy. The sides being all 1, then if that altitude is bisecting that base there, that means we've got a half. And now I just need to find the length of the altitude. And we all know from the right triangle, we've been using it already, Pythagorean theorem. So let's just call, maybe I'll just call that y. So let's use the Pythagorean theorem to find what y is. So y squared plus 1/2 squared equals 1 squared. So y squared is going to be 1 minus 1/4. Y squared equals 3/4. And yes, when you take the square root, it's usually plus or minus, but we're just going to be talking about a positive length here in a triangle. So we're just going to say positive √3/2. So what was the point of that? Well, I wanted to remind you of the ratios of the sides in a 30, 60, 90 triangle. So let's, so let's put this in a unit circle here. So say, maybe I'll make it here. We'll say we have this angle that's 60 degrees. And if I create a triangle here by dropping this altitude down to the x-axis, so we're going to create a right triangle. This is going to be a 30, 60, 90 triangle. And why is that helpful? Well, that can give me this x and y coordinate of this point here because I know the ratios of the sides. Again, we're talking about a unit circle. So this would be 1. Opposite 30 we said is 1/2. And opposite 60 is √3/2. So what's the x and y coordinate of this point? Well, the x coordinate is 1/2 and the y coordinate is √3/2. I could do the same thing if the angle created by dropping that altitude to the closest x-axis. If that had been 30, the x and y coordinate would have changed there. If it was 45, I'm going to have different ratios. So let's talk about the 45, 45, 90 triangle. And we're soon going to see where this all comes into play. But right now we're just looking at the ratios of sides of special triangles. All right, let's do 45, 45, 90. So with the, again, let's think of the hypotenuse as 1, kind of like the R value in a unit circle. And in a 45, 45, 90, I know the legs are the same, so let's just call them x. And again, we can use the Pythagorean theorem to derive this ratio if we don't remember. So x squared plus x squared equals 1 squared. 2x squared equals 1. X squared is 1/2. Normally it'd be plus or minus, but we're talking about a length of a triangle, so we're going to say the square root of 1/2, or I'm going to say √2/2, rationalized. I mean, you could say 1/√2, but let's just rationalize this one. So √2/2, √2/2. Okay, so that means if I have this terminal side of an angle and the angle created with the closest x-axis is 45 degrees, then I have this that's illegible. If I have this 45, 45, 90 triangle, the unit circle, I'm going to have my hypotenuse be 1. Then it means opposite each of the 45 degree angles is √2/2. So the x and y coordinate would both be √2/2. Okay, so ratios of special sides of special right triangles, 30, 60, 90 ratio and 45, 45, 90 ratio. All right, so let's, remember we did that table where we filled in the ratios of the 6 trig functions at the quadrantal angles? We're going to do the same thing for filling in the ratios for the trig functions evaluated at 30, 60, and 45. All right, so let's go to the next page here. Now, what will be helpful for you in filling this out? Well, I think it will be helpful just maybe down below here. Just draw your 2 triangles. So we've got a 45, 45, 90. And again, you've got 1, √2/2, √2/2. And then for the, That doesn't really look like a 30, 60, 90. Well, just pretend it does. All right, so we've got the 30, 60, 90 triangle, and again in degrees. So we've got 1/2 root 3 over 2. All right, so using, and again, I put also radians because we're transitioning hopefully to using radians more and more. So fill in this table, looking at knowing what you know about the definitions in terms of, in this case, you can think about it like opposite over hypotenuse in terms of SOHCAHTOA, in other words, and fill in this table. So pause this and do that. All right, so once you've done that, let's see how we did. So for sine, we've got 1/2 root 3 over 2 and root 2 over 2. For cosine, we've got root 3 over 2. We've got 1/2 root 2 over 2. Tangent should be root 3 over 3, root 3 and 1. Cosecant is 2 root 3 over 3. Then we've got root 2. Secant will be 2 root 3 over 3, 2 and root 2, and then finally cotangent root 3 over 3, and 1. All right, so make sure that table is correct. Okay, so finally, obviously we're not just going to be evaluating angles that terminate in the first quadrant. So let's talk about what happens when we are terminating in a different quadrant. And what we want, we're still going to be creating a triangle, and by doing that, and how we create that triangle is we're going to, from the terminal side, drop the altitude to the closest x-axis. So that's really important. The reference angle that we're going to refer to is the angle formed from the terminal side to the closest x-axis. So all I want you to do in example 3 is, yes, you've got to figure out where that angle is terminating, and I want you to find the reference angle. Again, it's the acute angle. Remember, acute is between 0 and 90 degrees, and we're talking in degrees, between the terminal side and the closest x-axis. Okay, so let's do a few here to get an idea of what's happening. So for 135, so 135 is terminating in the second quadrant. So it'd be here, 135 degrees. To create my triangle, I'm always dropping down to the closest x-axis, which would be here. And so what is that reference angle? Well, it's going to be 180 minus 135, or 45 degrees. So the reference angle here is 45 degrees. Something like 218. We're now into the third quadrant. Again, well, that's not that exact, but in terms of where that angle actually terminates, but in the third quadrant, but drawing my altitude here. So in this case, to find that acute angle formed from the terminal side and the closest x-axis, it'll be 218 minus 180, or 38 degrees. So the reference angle here would be 38 degrees. Let's do one, actually, I'll leave you to do C. Again, you form from the angles from the terminal side to the closest x-axis. Let's do 1387. Now, this is where coterminal angles come into play, because I really want to figure out, where is this landing? What is this terminal to between 0 and 360? So I want to subtract multiples of 360, and when I do so, I realize, okay, it's coterminal to 307 degrees, which gets me into the fourth quadrant. And so again, to the closest x-axis. So my reference angle in this case will be 360 minus 307. So it's this angle here formed, which is 53 degrees. Sometimes the angle is a reference angle. Like in part E, 47 degrees, well, that is the reference angle. When it's a quadrant 1 angle, it itself is the reference angle. If we're talking about negative 225, remember I'm now going to go clockwise. This would be negative 180. Negative 225 would land in quadrant 2. And once again, the reference angle is the distance between the terminal side and closest x-axis. It's that angle formed. So in this case, it would be a 45-degree angle. Reference angle is always positive. It's acute, between 0 and 90 degrees. Okay, so now the key to when we are evaluating the trig functions at particular angles, we're really looking at the reference angle. But what quadrant it in matters, because that will determine if my x and y coordinate, if they're positive or negative. So let's do some examples here. And in this case, I'm gonna show you when I do these examples, kind of two ways to think about it. Again, I talked about the way I learned and kind of the way most people do it now, I would say. So let's do what most people do now, and you may love that. I find most people probably do it that way. But then I want to talk about the way kind of I was trained to do it. All right, go. So find the exact value of each expression. So I want to find what the sine of 120 is. Remember, sine is y over r. All right, or in terms, if we're talking about a triangle, it's opposite over, if we want to talk about it in terms of right triangle, it's opposite over hypotenuse. So let's draw where 120 is. 120 is terminating in quadrant 2. The reference angle is 60 degrees. And I want to find the coordinates of this point, because finding the coordinates of this point, and I'm going to make it so we're going to have it so that r is 1. So we're going to think about if I had this unit circle going, intersecting this point on the terminal side. So we're going to have r be 1. And I've got this 30, 60, 90 triangle. And in quadrant 2, and let's put the ratios to the side. Opposite 30 is a half. Opposite 60 is root 3 over 2. But I can't just write a half. I'm in quadrant 2. So in quadrant 2, the x value should be negative. So that's why it's going to be negative 1/2. So if I think of the coordinate of this point, it's negative 1/2 positive root 3 over 2. All right, so when I talk about sine of 120 here, I'm going to look at my coordinates, and I know r is 1, so sine is y over r, so it'll be root 3 over 2. So that's one way to do it. And again, a lot of people do this. They graph their little, they draw their little triangle in the coordinate plane, know the ratio, and then know that sine is opposite over hypotenuse, or y over r. What I do is very similar. First thing I do is sine of 120. I definitely need to know where that lands, and it lands in quadrant 2. And so because it lands in quadrant 2, I know that sine is positive in quadrant 2. Remember, we talked about all students take calculus. So in quadrant 2, sine is positive because y is positive there. So I know my ratio is going to be positive. And then I say that sine of 120 is going to be the same as the positive sine of the reference angle. So it's the same as sine of 60 degrees because 60 is my reference angle. And then I have either memorized, which I have by now, or I draw on my page my two special triangles. And I just refer to them. So instead of creating a triangle in a coordinate plane for each problem, I've got my two triangles written on my page, or I just know them, and I refer to them. So again, I realize 120 is in quadrant 2 where sine is positive, so I know it's going to be equal to sine of 60 and the positive of that. So it's going to be equal to sine of 60, in other words, which is when I go to my triangle, I look at 60, and the sine of 60 is opposite over hypotenuse, so root 3 over 2 over 1. Okay, let's do another. That was a lot. A tangent of 11 pi over 6. Okay, so I know everybody's going to want to convert that, or many of you want to change this to degrees. I'm going to ask you to try not to. It will be helpful to know that pi over 6 is 30, pi over 3 is 60, and pi over 4 is 45. So if I have 11 pi over 6, that's a multiple of 30 degrees, or a multiple of pi over 6. And how do I know where it is? Well, 2 pi, which is equivalent to 360, would be 12 pi over 6. So it's 1 pi over 6 less than that. So again, I'm going to repeat that. 12 pi over 6 would be 2 pi, which would be a full revolution. 11 pi over 6 is just 1 pi over 6 less than that. So it's landing in quadrant 3. It's 1 pi over 6 less than it. So my reference angle is going to be pi over 6, which is 30 degrees, and which means I have a 30, 60, 90 triangle, so pi over 6 and pi over 3. So then I put in my ratios. So y is negative in quadrant 4, so it'd be negative 1/2, and then positive root 3 over 2. So tangent is y over x, so it's going to be negative 1/2 divided by root 3 over 2, which is going to be negative divided by negative 1/2 divided by root 3 over 2, which is going to reduce to negative 1 over root 3 or negative root 3 over 3. How I would do that, again, create the triangles, no problem in doing that, but I would say if I were doing this, how I would once I figured out it was in quadrant 4, I know tangent is negative in quadrant 4, so I would say tangent of 11 pi over 6 equals negative tangent of what the reference angle is. And the reference angle is pi over 6. The nice thing about radians, the reference angle just jumps right out at you, especially if it's a multiple of pi over 6, pi over 4, pi over 3. It's literally in there. So tangent of pi over 6. So then I would just look at my little triangle I had. These triangles I have over here. And I go to pi over 6, which is 30 degrees, and tangent is going to be 1/2 over root 3 over 2. It's going to get the exact same thing as when you draw the triangle in the coordinate plane, but I already put the negative in front, so I knew it was going to be negative based on the fact that it is in quadrant 4. Either way, a lot of people draw the triangles in the coordinate plane, and it's going to be slow going at first. But I promise the more you do this, the better and quicker you'll get at it. Okay, so try those. You're going to have a lot of practice with these in the homework section. And the last thing I want to do with you is now going backwards. So what if I give you the ratio and you have to then give me the angles that meet that condition? So, for example, and I put a restriction on it. I said that I want the angles between 0 and 2 pi. By the way, if I said between 0 and 2 pi, that means you're giving me the angles in radians. If I said 0 to 360 degrees, you'll give your answers in degrees. So, again, it's helpful to have these two triangles kind of somewhere. So sine of an angle equaling negative 1/2. So a few things you want to think about. First of all, the fact that the ratio is negative. If sine is negative, what quadrant angles will you be giving me? Well, if sine's negative, that means the y is negative, and that means I'm in quadrant 3 and quadrant 4. So you're going to give a quadrant 3 angle and a quadrant 4 angle. That's one thing you have to think about. The other thing you have to think about, and this is where looking at the triangles will be helpful, when I take the sine of what reference angle do I get a half? So what angle is opposite over a hypotenuse equal to a half? And I look at my triangle and I see, okay, that's 30 degrees. Or in other words, because we want radians, pi over 6. So my reference angle is pi over 6. Okay, So what is the quadrant 3 angle then? As I told you before, I like radians. I think they're easier and it takes some getting used to. But if I think of a quadrant 3 angle, I need the reference angle to be pi over 6. So I need the distance between the terminal side and the closest x-axis to be pi over 6. What is that angle in degrees? What I think about is it's one more pi over 6 than pi, or in other words, it's pi plus pi over 6. So think about it as 6 pi over 6 plus pi over 6. So it's 7 pi over 6. It's one more pi over 6 than pi. In quadrant 4, same idea. This is going to be pi over 6. That's the reference angle. So 2 pi in terms of 6 would be 12 pi over 6. So I want one less than that. So I want 11 pi over 6. So that's what you're doing there. Let's do another. Let's do cosine of an angle is root 3 over 2. First thing I think about is, okay, cosine is positive in what quadrants? Well, I want where x is positive, so I want quadrant 1 and quadrant 4. Then I think about, okay, what's the reference angle? Looking at my special triangles, which acute angle, when I take the adjacent over hypotenuse, do I get root 3 over 2? And that's going to be 30 degrees or pi over 6. Well, one of my angles is going to be the quadrant 1 angle in this case. Well, that is the reference angle, so pi over 6. That one's easy. Quadrant 4, we just talked about. It's 1 pi over 6 less than 2 pi, or less than 12 pi over 6, so 11 pi over 6. Okay, what about if the ratios are what about, I want to do part D. We're going to skip C for now. I'm going to have you do C on your own. So you can pause it and do it now, or and check your solutions against mine, or you can do it later. But so D, what about a reciprocal function? Secant of an angle equals negative root 2. So some people like to change that to a cosine in this case, to the standard trig function rather than the secant, so to its reciprocal. Totally fine to do. So if you wanted to do that, you would say cosine of an angle. If secant of the angle equals negative root 2, it means cosine of the angle is negative 1 over root 2 or negative root 2 over 2. Either way, cosine and secant are both negative when x is negative, so quadrant 2 and quadrant 3. The reference angle, so whenever I see root 2, I think, okay, that's the 45, 90. So the reference angle there has got to be 45, or pi over 4. In quadrant 2, it would be 1 pi over 4 less than pi. So think of 4 pi over 4 minus pi over 4, so 3 pi over 4. Quadrant 3, it's 1 pi over 4 more than pi. So 4 pi over 4 plus pi over 4 would be 5 pi over 4. Okay, so both ways. Here, given an angle, evaluate the trig function at that particular angle, and the other way around. Given a ratio, find the angle when I take a certain trig function of it that gets me that ratio. We're going to skip example 6, and you're going to similarly skip the last 2 homework problems relating to using the calculator, because I want to do that, kind of have that bleed over to the next class. So make sure you bring your calculator for the next class to talk about how to do some of the stuff on the calculator.